Hi there, Miss Barbara here. I hope you're doing well. Today's lesson deals with antiderivatives, which are often called indefinite integrals. Many operations in mathematics have reverses: addition and subtraction, multiplication and division. In this lesson, we learn how to find a function from derivatives. This reverse operation for differentiation is often called antidifferentiation. The process reconstructs the function from the derivative. For example, we can determine a company's total profit if we know its marginal profit function. The learning objectives for this lesson are: be able to compute indefinite integrals, be able to verify antiderivatives, be able to solve initial value problems, and finally, be able to solve applications of antiderivatives and indefinite integrals. A question often asked of business majors is, where is it used? Here is an example problem. A bottle manufacturing company has determined their marginal cost function as C prime of x equals 3x squared minus 24x plus 53. Find the cost function if the monthly costs at zero output are $30,000. What is the cost of manufacturing 4,000 bottles per month? How about 8,000 bottles per month? X is in thousands. Antiderivatives. A function denoted by uppercase f is an antiderivative of a function denoted by lowercase f if uppercase f prime of x equals lowercase f of x. Example, find three antiderivatives of f of x equals x cubed. Hint, what functions can you take a derivative of to get the function f of x equals x cubed? Now, as we begin this problem, let's recall that anytime you take the derivative of a power function, you decrease the power of the function by 1. So if we are going in the opposite direction, my first attempt would be to let capital F of x equal x to the fourth. So let's see what happens when we take the derivative of that first attempt. We get f prime of x equals 4x cubed. We're off by a factor of 4. So how about if we divide by 4? So my second attempt will be f of x equals 1/4 times x to the 4. Then when we take the derivative, f prime of x is equal to 1/4 of 4x cubed. We can further simplify and that becomes x cubed, and that actually works. Now we've got 1, we still need 2 more. Let's consider the question. The derivative of what is 0? Well, the derivative of every constant is 0. The answer, any constant. How about 7? So my second function will be f of x equals 1/4 x to the 4th plus 7. Let's take the derivative, and I get f prime of x equals 1/4 times 4x cubed plus 0, which gives us x cubed, and that works. So how about if we just pick any constant? That is, f of x equals 1/4 x to the 4th plus c, where c is any constant. So now when we take the derivative, we get f prime of x equals 1/4 times 4x cubed plus 0, which is x cubed, and that works. This adding 1 to the power to find the antiderivative, it probably generalizes. The symbol that looks like a stretched out S is called the integral symbol. It means to find the derivative of the function to the right. So we can write integral of x cubed dx is equal to 1/4 x to the 4th, but remember we must have plus c, where c is any constant. Theorem, antiderivatives. If the derivatives of two functions are equal on an open interval ab, then the functions differ at most by a constant. Symbolically, if uppercase f and uppercase g are differentiable functions on the interval a to b, and uppercase f of x equals uppercase g of x for all x in the interval a to b, then uppercase f of x equals uppercase g of x plus c for some constant c. C represents a real number and is called the constant of integration. Antiderivatives and definite integrals formulas. Remember, antiderivatives and indefinite integrals are interchangeable terms. Constant rule. The integral of k dx is equal to k times x plus c for k, any constant. That is, the integral of any constant is that constant times x plus an arbitrary c. Power rule. The integral of x to the n dx is equal to x to the n plus 1 divided by n plus 1 plus c, provided that n does not equal -1. So a good question to ask is, what happens if n does equal -1? That takes us to the next rule. Natural logarithm function rule. The integral of 1 over x, that could be written as x to the minus 1 dx is equal to the natural log of x plus c, provided that x does not equal 0. And finally, the exponential function rule. The integral of e to the x dx is equal to e to the x plus c. Example. Find each indefinite integral. Part A, the integral of 7 dx. Let's note, 7 is just a constant, so the integral would be 7x plus c. Part B, the integral of x to the 12 dx. We'll use that power rule again, which will give us 1 over the power plus 1, so 12 plus 1, times x to the power of 12 plus 1 plus c. Let's simplify that, and we'll get 1 over 13 times x to the 13 plus c. Part C, the integral of x to the minus 5 dx. The power rule remains the same regardless of the sign of the number or whether or not it's a fraction, as long as the power is not -1. So let's apply the power rule again here, and we'll get 1 divided by the power, which is -5 plus 1, times x to the power of the existing power, which is -5 plus 1, and don't forget the c, plus the constant. Let's do the arithmetic, and this will simplify to 1 divided by -4 times x to the -4 plus c. And if you wanted to, you could write this as the negative of 1 over 4 times x to the 4. Notice that the power is positive if you move it to the denominator, plus c. Let's continue. Part D, the integral of x to the power of 2/3 dx. We use that power rule again, and we'll write that as 1 over 2/3 plus 1, and then x to the power of 2/3 plus 1. Don't forget the plus c. We have to have that for every indefinite integral. And simplify, getting a common denominator that'll be 1 over 5/3 x to the power of 5/3 plus c. And then let's flip that constant, and we'll have it as 3/5 times the cube root of x to the 5 plus c. Now let's go to E, the integral of the cube root of x squared dx. When you see a problem written in radical notation, the first thing to do is express that as a power to a rational number. So we would rewrite this as the integral of x to the power of 2/3 dx. And let's observe, we already did that in the previous example. Example 3. Find each antiderivative. Part A, the integral of x to the minus 1 dx. We'll go ahead and write that as the integral of 1 over x dx. And simplified, the integral of 1 over x dx would be the ln of x plus c. Now let's go to part B, the integral of e to the x dx. Now, if you remember, the derivative of e to the x is just e to the x, and we're undoing it, which gives us the same thing. So the integral would be e to the x plus c. Now let's look at some properties of antiderivatives and indefinite integrals. The first one states that the integral of k, that's any number times a function, dx is equal to, you could take that k out of the integral sign and just multiply it to the integral of f of x dx. And the integral of the sum or difference of two functions is equal to the integral of one plus or minus the integral of the other function. Example, find each antiderivative. The integral of x cubed times the quantity x squared plus 2x minus 8 dx. To do this problem, we're going to do the algebra first. That is, distribute that x cubed to each of the terms in the parentheses. And that'll give us the integral of x to the fifth plus 2x to the fourth minus 8x cubed dx. Now we can use the property that lets us take each part of the integral separately, and also the property that lets us take the constant outside of the integral symbol. The integral of x to the fifth would be 1 over 5 plus 1, x to the power of 5 plus 1. Now integrate 2x to the fourth. The 2 gets multiplied, it's the constant. And then take the integral of x to the fourth. That would be 1 over 4 plus 1, x to the power of 4 plus 1. Then one term left. We'll have minus 8, and we want the integral of x cubed, so that'll be 1 over 3 plus 1 times x to the power of 3 plus 1. And don't forget the plus c. Now let's do some of the arithmetic. We'll get 1/6x to the sixth plus 2 times 1 over 5 x to the fifth minus 8 times 1 over 4 x to the 4 plus c. Then one more round of simplifying, which will finally give us the integral of 1/6 x to the sixth plus 2/5 x to the fifth minus 2 times x to the 4 plus c. Find the integral of, in the numerator, 5x to the fifth plus 3x to the sixth e to the x, all divided by, in the denominator, x to the sixth dx. We need to do some algebra first. Let's do term-by-term division. So this would be written as the integral of 5x to the fifth divided by x to the sixth plus 3x to the sixth e to the x divided by x to the sixth dx. Now we can cancel some terms. The x to the fifth and the x to the sixth will leave one x in the denominator. That's for the first term. And for the second one, the x to the sixth and the numerator and the denominator cancel. Now let's write the simplified version, which will give us the integral of 5 over x plus 3e to the x dx. Let's integrate. We would get 5 times the integral of 1 over x is ln of x plus 3 times the integral of e to the x is just e to the x plus the constant. And finally, part C. We've got the integral of x squared minus 2x minus 15 divided by x minus 5 dx. Remembering that there's no such thing as a quotient rule for integration, we need to do some algebra first. So let's factor the numerator. That'll give us the integral of x squared minus 2x minus 15 is factored to x minus 5 times x plus 3 divided by x minus 5. We see common factor of x minus 5 in the numerator and the denominator. And so we'll cancel that common factor. Now let's write this integral again. And we get the integral of x plus 3 dx. Now we can integrate, and that'll give us 1 over 1 plus 1, because x's power is understood to be 1, times x to the power of 1 plus 1 plus 3 times, and the integral of a constant is just that constant times x, and don't forget the plus c. Let's do the last bit of arithmetic and we'll get 1/2 x squared plus 3x plus c. Let's find each of the following. Part A, and let's pay particularly close attention to the notation. d dx, that's take the derivative with respect to x of the integral of the quantity 3x squared minus e to the x squared dx. Let's note the derivative of the integral of a function and the integral of the derivative of the function gives the function. And so when we take the derivative of the integral, we end up with the function itself, which would be 3x squared minus e to the x squared, and don't forget the plus c that must be included with every indefinite integral. Now to continue with b, we need y by itself, so we're going to take the integral of both sides. That is, we want the integral of dy dx, and set that equal to the integral of 3x to the minus 1 plus x dx. Let's begin with the left-hand side. The integral of dy dx, that's just y. We undid it, and we're going to set that equal to the integral of, and if it's helpful, look at the x to the minus 1 as 1 over x. So you have 3 times 1 over x plus 7, and we'll integrate. Y equals 3 times the integral of 1 over x is ln of x plus the integral of 7, which is just a constant. We put an x with it, so we have 7x, and don't forget the plus c. Initial value problems. In some applications, the constant of integration is of great interest. In such cases, we can solve for the c if we are given a point that is a solution of the antiderivative. This particular point is called an initial condition. Example, a company determines that their marginal cost function as c prime of x equals 3x squared minus 24x plus 53. Find the cost function if monthly fixed costs at zero output or $30,000. What is the cost of manufacturing 4,000 bottles per month? How about 8,000 bottles per month? X is expressed in thousands. Solution. This is an initial conditions problem with the initial point 0, 30. The initial cost is the fixed cost. To solve for the cost function c of x, we need to integrate the derivative c prime of x dx. And so that'll be the integral of 3x squared minus 24x plus 53 dx, and let's integrate. The integral of 3x squared would be x cubed. Remember, we're going to do 3 times 1 over 2 plus 1, that's 3 times 1/3, x to the power of 1 more than what's there, that would be 3, minus, and then the 24x, if you do the power of 1 and bring it down and add to it, it's going to be 24 divided by 2, that gives you 12. X squared, and finally plus 53x plus. And in this problem, I'm going to use k for constant to not confuse it with the c we're using for the cost function. Now we're going to solve for k. We have c of x equals x cubed minus 12x squared plus 53x plus k. The initial condition is 0, 30. So we put in 30 for the cost. 30 is equal to, and then put in 0 for the x's. 0 cubed minus 12 times 0 squared plus 53 times 0 plus k. That gives us 30 equals k. The cost function is c of x equals x cubed minus 12x squared plus 53x plus, and where the k was, we replace it with 30. To compute the cost of making 4,000 bottles, we put in 4. Remember, x is expressed in thousands, so you have 4 cubed minus 12 times 4 squared plus 53 times 4 plus 30, and that's equal to 114. And the cost of producing 8,000 bottles we compute at 8, so c of 8 is equal to 8 cubed minus 12 times 8 squared plus 53 times 8 plus 30, and that's equal to 198. Now remember, these numbers are in thousands. So the cost of 4,000 bottles is $114,000, and the cost of 8,000 bottles is $198,000. Let's connect this calculus to business. Provided for you is a graph of both the cost function and the marginal cost function. The cost function has a concave down portion where the derivative is decreasing, and the cost function has a concave up portion where the derivative is increasing. Why is the graph of the cost function steeper at both ends than in the middle? Here we get a business explanation for the calculus output. Manufacturing plants are often not as efficient or as cost-effective at the low and high levels of production.